Alright, during the discussion of previous video, while we were trying to find the direction of origin of motional EMF, one interesting actually happened. Out of nowhere, the term electric field popped up. We were never actually expecting that, right? But suddenly a term electric field popped up in our discussion, right? So just to do a quick review, let's see how that happened, and then we'll also in this video try to explain what is the property of this electric field that we suddenly got out of nowhere in the discussion of magnetism. Surprising a little bit, but yeah, let's see. Fine. So what happened was, you have this CD portion of the rod, the CD portion of the sliding rod from motional EMF. So this is the C end of the rod, this is the D end of the rod, and the rod was actually moving to the left with a velocity of V in a uniform magnetic field of field strength B, right? And what happened was, the electron, this is one such electron here, this right here is one such electron. That electron along with the rod is moving towards left, and with this electron moving towards left, it's like a motion of charge in the presence of uniform magnetic field. When that happens, there will obviously be a magnetic force, and that magnetic force turned out to be in upward direction. You can do a little cross product and find that this direction of force on the electron would be upward direction. This yellow color line that you see here in upward direction. Alright, and if the magnetic force was in upward direction, that led to sort of excess of electrons near the C end of the rod, and deficiency of electron near the D end of the rod, right? So with the excess of electron, the C end is actually gaining the negative potential, and the D end of the rod is actually gaining positive potential. And C end being negative potential and D end being positive potential is as good as having a battery connected between C and D. Look at this battery right here. So you have, this is the C end, this is the C end, and this right here is a D end. And as we have already realized that C end is going to be negative, so the negative terminal of the battery is here, and the positive terminal of the battery is here, right? So it's as good as having a some sort of source of EMF between those two. And with all this, I've not reached here yet. I've not reached the topic of electric field yet. But yeah, now listen. What happened was, as a result of electrons moving upwards, we know this. If electrons are moving upwards, if electrons are moving in this direction, this means that conventional current, the conventional current I, should be in opposite direction, right? So in this case, actually, if the electrons are directed upwards, the current must be in downward direction. So I'll just show that this is the direction of current, and in fact this is in accordance with the Fleming's left hand rule or the Lenz law as the direction of current predicted by Lenz law. So this actually is correct, except now for the real discussion. We know that if there is non-zero current, in a conductor, it must be due to electric field. It must be due to electric field inside the conductor. You already know this. Conductor. Alright. However, we don't have any source of electric field here, but we still got some electric field, and according to the knowledge that we've already acquired in current electricity, that if the current is in this direction, then the electric field which is causing the current must also be in the same direction. In fact, the direction of conventional current, this right here, the direction of conventional current and the direction of electric field are always same in a conductor. All right. This electric field, where did this come from? Now, the only logical, see, electric field can be in fact produced by having non-zero charges or creating potential differences, but none of that really happened. All those things are consequence of what? I think all of them were consequence of, yeah, you must be thinking, no, there is definitely a potential difference between C and D, right? Yes, but what was that? How did that arrive? How did a change of potential occur between C and D? That happened, if I'm not wrong, is due to changing magnetic flux. Let's say I change this term of changing magnetic flux to changing magnetic field. If I could write it as changing magnetic field, in fact, if the magnetic field is changing, definitely the flux will be also changing, right? So changing magnetic field, in a way I can say, gave rise to electric field. And this is as fundamental as one can get. You can't get any further fundamental than this. Yes, you could, a less depth statement of production of electric field would be, since there was a potential difference, there is electric field, because we already know this, that electric field E can be written as minus dV divided by dr, right? So basically potential gradient is nothing but electric field. Yes, I agree, and there is definitely potential gradient between C and D, and therefore we can say that there is electric field. But who in the first place caused that potential gradient? It was in fact the changing magnetic field, right? And therefore we can say that the changing magnetic field, time varying magnetic field, can give rise to electric field. And this was in fact is the greatest achievement of the Faraday's law. Yes, Faraday's law gave us an expression for EMF and everything, but the greatest achievement of Faraday's law was this statement right here, that a time varying magnetic field, or changing magnetic field, time varying magnetic field gives rise to electric field. And actually this electric field in fact is induced electric field. This is an induced electric field. And from here onwards, if I want to refer to our good old electric field, which we have already learnt in electrostatics, for that I'll be referring to, at least in this video, I'll be referring to that electric field which we have already learnt in the past. Not this one. This is induced electric field. This came as a result of varying magnetic field. The old electric field, which is produced due to the electric field that we have already studied, that electric field which is due to charges or different potential difference, that electric field I'll be referring to it as electrostatic field. So this one right here, which is as a result of changing magnetic flux, will be called induced electric field, and the electric field, the conventional, the usual electric field that we come across, I'll be calling that as electrostatic field. Alright, now then the natural question, why are we naming them different? And if someone is naming them different, should mean that there should be some differences between the induced electric field and the electrostatic field, right? So let's see, we can maybe in fact learn about that in properties of induced electric field. So let's see them one by one. Properties of induced electric field. First property is that induced electric field, just like the electrostatic field, is a vector quantity. So it is definitely a vector quantity. Second, in fact, instead of writing 1.1234, induced electric field is practically the same as the electrostatic field. It's exactly the same, except there is one small difference. We'll talk about that, and that difference makes the whole what do you call, makes the whole, the one difference makes the whole, what do you say, difference between them. That didn't really make sense, but yeah, that's an important difference is what I'm saying. Yeah, so practically the same as electrostatic field. Now for the difference, the third point is going to be difference, that unlike electrostatic field, the induced electric field can form closed loops. I'm going to write that in bold letters, capital letters. Can form closed loops. And since it can form closed loops, it is a non-conservative field. So non-conservative field. What is non-conservative field? That work done in a closed path is not going to be equal to 0 in such a field. What field? In an induced electric field, in the region of induced electric field, if you take a particle or a charged particle in a closed path, in such case work done will not be 0. So it is non-conservative field. So third and fourth points are actually the differences. Apart from these 2 points, they are practically the same. They're almost the same thing. But these two differences are they actually are huge. The 2 differences here, they make a lot of differences as a result of this. Why am I using the word differences a lot? Anyway, fine. I hope you get the point, right? And if you want to calculate the induced electric field, then we can do a little tweaking of basic Faraday's law. The Faraday's law basically looks something like this: that the EMF E is equal to minus d phi divided by dt, the rate of change of magnetic flux, d phi b, if you will, right? This is Faraday's law. But we already know the relation between EMF and electric field. What is that? I think I can write electric field E as minus dE by dr. Instead of dV by dr, I'm writing dE by dr, because EMF and potential differences are the same thing as long as there is the internal resistance is 0, right? So I can, instead of dV by dr, I can write it as dE by dr. If I cross multiply E into dr, electric field E into dr is basically minus dE. And if I do a little integration to this on both sides, integration of dE is going to be the EMF, and that is going to be equal to minus E dr, or in fact you can write it as E dot dr, right? So E dot dr is equal to EMF. Don't get confused between the capital E and this E. This is EMF, this right here is EMF, and this is electric field. Anyway, now look at this equation. I don't know, let me call this equation 1 or something, and this equation, say equation 2 or something, right? If I combine these two, I can in fact write like this, that integral E dot dr is equal to d phi by dt. So you can in fact calculate the induced electric field using this expression right here. You can calculate using this expression, right? So yeah. Those are the properties of induced electric field. And more than the similarities are like they're practically the same. There's no similarity. Please remember the differences between induced electric field and your good old electrostatic field. Alright, I hope that helped. And in the next video we'll be discussing about the power considerations, as in if actually just listen to this part carefully. Actually, for any law that anyone has come across has to pass one test in physics always, that it should obey law of conservation of energy, law of conservation of charge, and law of conservation of momentum. In this case we'll be focusing on law of conservation of energy. Actually, any law that can pass law of conservation of energy is only then eligible to be called a law, right? So we'll be taking Faraday's law of electromagnetic induction through the test of conservation of energy law, and if this satisfies, then all the discussions that we have made over previous few videos is going to be actually valid. And in fact, in the next part we'll be trying to find out if Faraday's law is in agreement or is in accordance with law of conservation of energy or not. It has to be because Lenz's law in fact was in accordance with that, so it must be. But yeah, we'll see how that turns out to be true mathematically. All right, thank you.